before I begin the point of today's lecture, there's something, actually a rather practical discussion that I want to say about work. It's absolutely essential. Because when work appears in our actual problem solving, it's a very pragmatic discussion that I want to have. It appears in various forms, from its very most general form by definition to a very simple, straightforward form that is more common and is taught in lower level science classes, and sometimes it's difficult to see how these things are related. It's a very practical discussion about work, because how I've defined work in the previous lecture is that the work done is equal to the integral of the force dotted into the displacement. And this is the most general form of the work that I can possibly write. Because the force can point in any direction in three-dimensional space. And here I have it in the scalar product with the displacement in three-dimensional space. So this is quite arbitrary. It can cover absolutely any situation. And because I'm doing an integral with dr, it means that the force can change in any way over the course of the integral. The force can change in magnitude and change in direction. So this law for the work, this definition of the work, makes it possible for me to calculate how much work is done in any possible physical context with any possible force. So I guess I would say that this is the most general force of the work. And now I'm going to specify it all the way down to middle school physical science class on this end as I break it down. So here it's the integral of the force dotted into the displacement. It's a three-dimensional version of the definition. But of course, there are situations where I'm calculating only in one dimension, because often there are constrictions on the motion of a physical system, and I find that I'm solving a problem where this is constrained to one dimension, and so I could write this as the law, where I've simply chosen the x-axis to be that direction. Since coordinate systems are arbitrary, I can do that. So I've taken a three-dimensional definition of work and I've made it a one-dimensional definition of work because the system I'm applying it to is one-dimensional. And so now I'll evaluate this dot product here. This is the force dotted into the displacement. What that means, quite naturally, is that it is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Now, I've been really careful here to write the magnitudes of each and whatnot. I wouldn't typically write that. It's a lot of extra notation. But what it does is it appreciates the fact that it is only the component of the force that is in the direction of the displacement that does work. The other component in that two-dimensional coordinate system does no work because it is perpendicular to the displacement. So what I have here then is in the case, or when the angle between the force and the displacement is 90 degrees, the cosine of 90 is 0 and no work is done. So since only the component of force in the direction of the displacement does work, I'll consider the case where the cosine of the angle is the cosine of 0 degrees, which is in fact equal to 1. And then the work becomes the integral of f dx. I'm becoming more and more specific as I go. And so I have a force that is in the direction of a displacement along the x-axis. It's a one-dimensional problem with a force that points entirely along the x-axis. And this is how I would write the work. But imagine that that force was constant in magnitude for the entire displacement. If the force is constant in magnitude for the entire displacement, then it need not be in the integral, and I could write this as the force dx, or force times the integral of dx. And if it's the force times the integral of dx, I know what the integral of dx is equal to. It's simply the displacement, delta x. So the amount of work that's done in a one-dimensional problem with a constant force is the magnitude of the force multiplied by the magnitude of the displacement, dx. Well, very often, the displacement, if it's in one dimension and the thing doesn't turn around at all, that's simply the distance that a thing travels, and the work becomes f times d. And then I take it all the way down to the point where I'm teaching it to small children, and I say the most specific case of work is that work is force times distance. And the reason why I bring this up to you, as I said, is very practical for problem solving, is that when I'm solving problems, I don't always need to trot out the most general form of the work. I don't need to start from here. If the force is constant, then I can start over here and appreciate that the force I'm using is always the component of the force that's in the direction of the displacement. So in your problem solving, a skill that you'll develop as you solve more and more problems is realizing when it has to be calculus and when it doesn't. Sometimes a failing when I'm grading exams written by physics students is that they jam calculus in way too early. Not everything is a calculus problem. This is our most general form of work because the force can vary in magnitude and direction in three-dimensional space. That's not always the problem that you're solving. So the reason why I've done this, and why I've written it out this way, is so that we can appreciate that the work sort of comes in many forms when we're trying to solve problems. And I want you to appreciate the essential idea of being able to write that through. As I was introducing the notion of kinetic energy, actually defining the kinetic energy as 1/2 mv squared, is an energy associated with the motion of an object. And I said that, my definition of energy in general was energy is a number that I can calculate that has some universal properties as a symmetry that I can take advantage of. And I haven't defined enough yet that I can exactly see the way that symmetry is going to play out, because I mentioned in that discussion that there is another form of energy called the potential energy, and that the potential energy comes in a profusion of forms. And so now I would like to begin to develop that and flesh it out. I think that some of you are aware that potential energies are associated with forces and the action of forces on physical systems. Any of you have ever had the chance to calculate a potential energy, like the gravitational you've done, know that each potential energy is associated with some kind of force, but not just any force. The potential energies that we'll derive in our physics are associated with special forces called conservative forces. It's kind of a strange thing to me as I lecture about energy, that you say conservative forces, and it's a mystery what the name is. We don't realize fully why they should be called conservative forces till a little bit later in the lecture series. Maybe 3 lectures from now, it'd be abundantly clear. Conservative forces have very specific definition in physics. A conservative force has 2 requirements. The first is that a conservative force can depend only on position. Now, in Newton's second law, there's no restriction on what forces can depend on. Indeed, we've just recently had a good time working with forces that are velocity dependent, for example. And in a sense, the frictional force is direction dependent, because the friction force depends on which direction the motion is, because the friction force opposes the relative motion of surfaces. And I could also imagine some friction forces that might depend on other variables as well. I can imagine a force that depends on time. I can use an electric force to apply, or an electric field to apply a force on a charged particle, and I can vary that electric field in time. So I have a force that is time dependent. But my first requirement for conservative forces is that a conservative force must only be position dependent. And I'll elaborate on that in every case where I derive a potential energy from a conservative force. Also, the second condition, and the one that is most important for our problem solving going forward, is that conservative forces must be independent of path. I have to be very clear about what I mean. Imagine that I have a particle of some mass, I suppose. Well, it has to have a mass because I can't define the force without it having some inertia. And so here it is at position 1. And then later on, I find that it's at position 2. If I presume that it started from rest, there must have been some acceleration of the action of some force that caused that. So consider the force that moved the object from position 1 to position 2. Imagine that that force did so along a path from 1 to 2 like this. And I made that up. It's simply an arbitrary path between 1 and 2. Or I could certainly go in a straight line for 1 and 2. That could naturally happen. Or I could do something more elaborate, more sophisticated to go from 1 to 2. That is, I have these 3 paths, call them, I guess, A, B, and C. And I can go from position 1 to position 2 with a force acting. Now, along that path, the force does work. According to our general definition of work, the work is equal to the integral of the force dotted into the displacement. And in situation A and C, the displacement is very sophisticated indeed, because it's quite elaborate, and I would have to perform an integral along A and B because the direction of the force and the direction of the displacement would change relative to each other, and it would be very complicated. So I would do that calculation in tiny steps and add up the work from one place to the other. But along B, it would be easier because I would only probably need to take one component from position 1 to position 2, and I could calculate that. At any rate, my condition on a force that is conservative, that the work done from 1 to 2 is the same along each path. Before I give you an example of a force that would follow this rule, let me give you an example of a force that doesn't. The friction force is a non-conservative force. It does not meet this condition. It doesn't meet the first condition either, because the friction force doesn't simply depend on position. It depends on direction as well. But it doesn't meet my second criterion because imagine that I push some heavy object from 1 to 2. Say we're looking at these paths from above. the object has a weight, and therefore there's a normal force, so a friction force exists, and I push it along. In order to push it along the path, I have to exert a force at least equal to the kinetic friction that opposes. But that kinetic friction force changes direction, so how much work would be done? It would be the constant friction force, mu times the normal force, so mu mg, whatever you like, times the length of the path that I travel from 1 to 2. You can clearly see on my diagram that these paths, A, B, and C, are not of equal length. So the amount of work done by friction along that path is not the same for each path A, B, C. It's not the same. And so friction is not a conservative force. Friction is not a conservative force. Viscous drag is not a conservative force because, like friction, it's direction dependent. The viscous drag force always opposes the direction of the velocity. And since this thing goes around in all kinds of directions as it goes from A to B, that means that the viscous drag is not a conservative force. But beyond that, how do I know going from 1 to 2 that the velocity doesn't change? The velocity may very well change as I go along paths A, B, and C, in which case the magnitude of the viscous drag force would change along those paths. Viscous drag is not a conservative force. So let me invent a force that is conservative because it depends only on position and will have this property that I seek, and I'll demonstrate how it is so. It is an absurd force that practically does not exist in nature. It is a force that I'll simply call F that is constant in magnitude and constant in direction. You might say, well, Shiley, there is such a force, the force of gravity. Everywhere that I go in the room, the gravity is downward and the same magnitude everywhere. Well, that's not true. We know that as I go away from the surface of the Earth, the gravitational force weakens. So saying that the gravitational force in this room is uniform is an approximation. It's not really true. The gravity weakens from the floor to the ceiling, but it doesn't weaken by that much. So it's okay to do that approximation. But what I'm going to imagine is a force F that is absolutely constant in magnitude and direction everywhere in the universe, and I'm going to allow that force to do work from an initial position to a final position, and I'll see what kind of result I get for calculating the work. And along the way, it gives me an opportunity to talk about how work is calculated. This general situation that I've drawn here is a bit too complicated. So what I'm going to do is I'm going to draw it again with paths that are a little simpler, so it'll make the discussion easier. I'll start at position 1 here, and I'll finish at position 2, and I'll give myself the advantage of this straight line path, because the straight line path between 1 and 2 is probably going to be easy for me to calculate or to make an argument. So the force is going to act from 1 to 2, and it can go along that path from 1 to 2. But I'll give it some other path so that I can compare the results that I get. Imagine it goes straight upward, up the board here, and I guess I'll call this y, the distance that it goes up vertically. Imagine xy coordinates is a sensible name for the thing. And then it goes over like this to position 2. And I'll call the distance it goes along to position 2, I'll call that x, right? Along the x-axis. So those are two distances that are traveled. A little bit of geometry that I can do to give some numbers, or, well, not numbers, but to give some definition to those displacements. So now what I'm going to do is I'm going to have this force act on the object. And so here it is. I'm going to draw it in position 1. The force that I'm suggesting is a force that is directed entirely along the y-axis. And I'm going to just call that force F. There's that force directed entirely along the x-axis. And I'm going to calculate the work done from 1 to 2, but I'm going to do it along these two different paths. And I'm going to see what sort of result that I get. So in order to calculate, I guess I'll call these paths, just as I did in my original, I'll call this path A and this path B. So imagine the work done over path A. Well, the thing about it is path A has two parts to the work. It has the work done from 1 up here to the corner, and then from the corner over to 2. So it does it in two parts. So I'm going to calculate that work in 2 goes. The work done along A is going to be the work on the first part, which is going to be from 1 to A. Well, that's easy to do. Now, I just did an argument about generalized work. Yes, I calculate that work as F dot dr. But now I have to think about how I can generalize that work. Notice that the force is entirely in the direction of the displacement upward. As I go from 1 up to the corner, the force is entirely in the direction of the displacement. So I need not calculate the most general form of the work. And by the way, the magnitude of the force is absolutely constant. And its direction is absolutely constant. So the integral is not necessary. All I need to do is to calculate the work done in that first part is to calculate, I'm doing myself a disservice here in the way that I've written this. All I have to do, I'm going to do this, I hate it, but I'm going to do it. All I have to do to calculate that work is to take the force and multiply by the displacement, which is equal to y. So the work done from 1 to the corner is Fy, but I'm not done yet. because there's an extra function of work that I have to do, which is the work done for the second part, which is from the corner to 2. Well, look what's happening when I get to the corner. When I'm up here, I'm going to draw this thing in an arbitrary. See, I've got my X there. I got to watch out for it, right? There's the force F. Notice that as I go along the top of this triangle here, that the force is perpendicular to the displacement. Well, if the work done on that second part is going to be equal to F dot dr, the force is perpendicular to the displacement. There is no component of the force in the direction of the displacement. This force does no work. A force that is directed perpendicular to the displacement does no work at all. So the work done by this part, or in this stage of it, in the first part and the second part, is going to be equal to 0. So the total work done along path A is just F times y. That's the amount of work that I do as I go from the first position to the second position along that path. What happens if I do it along path B, so the work done along B? Well, I'll calculate work the same way. It's the integral of F dot dr, but I have to be careful now. Do you see? Because as I go along B, the force is still directed straight upward because the force is absolutely constant in space. The force is still directed straight upward, but now it is not in the direction of the displacement. And you say, well, that's okay. All you have to do is find the component of the force in the direction of the displacement. Okay, I'll do that. Let me define in here on my diagram, the worst diagram that I've probably ever drawn in my career, the angle theta right there, which is the angle theta between the force and the displacement, same angle. So that angle there, I'm just going to do the integral of, well, I don't have to do the integral because the force is constant, so I'm going to do the force times the cosine of that angle. That gets me the component of the force that's in the direction of the displacement, and I'll simply multiply that by the displacement itself. Well, a little rearrangement of this shows me that this is F times R times the cosine of theta. You see, clearly R, I'm saying, is this hypotenuse of this. X squared plus y squared square root is R, the hypotenuse of that. Well, R times the cosine of theta, because this angle is interior here, R times the cosine of theta is the adjacent side of this triangle, which is just equal to y. And so what I discover here is that the work done by the force is just F times y. Demonstrating quite clearly here that if I go from position 1 to position 2 under the influence of this force, whether I go along path A or path B, the work done is the same. So it meets my second condition for a conservative force. It meets my second condition, meets the first and the second condition for a conservative force. We say, well, Shadley, I'm not convinced. I'm not convinced because these two paths, they were kind of special going from 1 to 2. Okay, let me give the arbitrary path. Path C from 1 to 2 is a path that is curved, arbitrary in shape. How then would I calculate the work from 1 to 2 along this arbitrary shaped curve? Well, let's choose an arbitrary position along the curve. Here is my force, once again acting in this direction. That's the force F again. I guess I should have written force F here, right? What a crowded diagram. There's the force F acting there. We say, well, your problem is that as you go along curve C from 1 to 2, the direction that you're traveling is changing. So the displacement is changing the whole time. Yes! So I'm going to have to perform an integral. But that integral is going to be F dot dr, a differential displacement along this curve from 1 to 2. So I'm going to be finding the component of the force in the direction of dr, which is the same as finding the component of r in the direction of f. Do it either way. The component of r in the direction of f, the component of dr, I should be saying, the component of dr in the direction of f is dy. So the work done along path C is going to be the integral of f dot dr, which is going to be equal to the integral of f dy, and since the force is constant, it's going to be F times the integral of dy. It's going to be F times y. See that? Generalized work, right? Understanding how work works. I trapped myself there. There was nothing I could do about it. So the work done around across through any arbitrary path, A, B, C, or any other path that I dream up, is Fy, Fy, Fy. The work done by this particular force, a very fictitious force, the work done by this fictitious force is independent of path. And so I declare it a conservative force. I declare it a conservative force. Therefore, since it is a conservative force, I can associate with it a potential energy. Conservative forces have potential energies associated with them because the work done by that force depends only on position and no other quantity. For example, it doesn't depend on velocity. If it depended on velocity, it would be conflated with kinetic energy. It's independent of kinetic energy. It's a kind of energy that depends only on the configuration of the system and no other. So, here comes an extraordinarily important theorem that will come up again and again in our physics every time we have occasion to derive a potential energy. The work done by a conservative force, which I'll call WC, the work done by a conservative force, I'll never write WC in the future, I just have to write it now because I have to distinguish between work done by conservative forces and work done by other forces, non-conservative forces, like friction, viscous drag, forces exerted by people.
There's another WC on the board.
No, that's true. I have another WC there, but make it a D real quick. No. How's that? Work done by conservative forces. Notation is important. Notation is important. Is equal to the negative of the change of the potential energy. A little bit of a cryptic statement now, but it'll become much clearer when I derive my first ever real physics potential energy, which I'm going to do right now. So I assert the relationship between the conservative work and the potential energy. This is sort of is going to be my definition of potential energy. This is what I mean, with the condition being that the work must be the work done by some conservative force. So the very first potential energy that I'm going to calculate is the gravitational potential energy. Gravitational potential energy, it has to be related naturally to the gravitational force. Is the gravitational force a conservative force? We'll consider the criterion. The gravitational force near the surface of the Earth is uniform everywhere in space. I know I just made the argument that it weakens as you go away from the surface of the Earth, but we're going to do this derivation with the assumption that it's uniform, just like the force that I just used in my example. The force I just used in my example was uniformly upward, and gravity naturally is uniformly downward. So the force of gravity depends only on the position, in the sense that it depends on nothing, not even position. That's what's a conservative force by that definition. Is the work done by the gravitational force independent of path? It's easy to convince yourself that it is, according to the demonstration that I just made. So, by the way, since the force that's doing the work can depend only on position, my potential energy can depend only on the initial position and final position, right? My potential energy can depend only on position, can't depend on anything else. You will never see a potential energy that depends on time. You will never see a potential energy that depends on velocity or any other physical quantity. Potential energies must depend only on position because it's a requirement of the forces which I calculate them. So if the work done is equal to the change in potential energy, it's quite simple. I simply have to calculate how much work is done by gravity. Since there's sort of a path independence thing going on here, imagine that I have an object of mass m. I need not do something fancy with the path. Let me simply apply a force upward, Fa, against the force of gravity, mg, and lift an object from an initial height, y0, to a final position up here, that's y. I'm simply going to lift it from here to here, and I'm calculate how much work is done by gravity. Now, if I lift it at constant speed, then the force that I exert upward, the applied force in my diagram, has to be equal to the force of gravity, right? Has to be equal to the force of gravity. So I'll consider that as I do this. So the work done is equal to the change in potential energy. Let me start with my work. Work is, in its most general form, the force dotted into the displacement dr. The force dotted into the displacement dr. Well, what is the force dot dr? Notice that the gravitational force is downward and the displacement is upward along the y-axis. So this is going to be the integral of the magnitude of the gravitational force times the magnitude of the displacement times the cosine of the angle between the gravitational force and the displacement. Well, the angle between the gravitational force and the displacement is 180 degrees. The displacement is upward. The gravitational force is downward. So it's the cosine of 180 degrees, which is -1. The cosine of 180 degrees is -1. And the displacement is entirely along the y-axis. So what I'm integrating here then is the force of gravity, mg, well, negative, because I picked up a negative sign, dy. So the work done by the gravitational force as I go from y0 to y, I put limits on the integration. I've never done that before. I don't think I'll ever do it again. I think it's ugly. Negative mg dy, well, the gravitational force is constant through the integral. So I'll pull it out of the integral. It's negative mg, the integral from y naught to y of dy. It couldn't be simpler to perform that integral. If I add up all of the differential y's, dy, I get the whole change in y, right? Delta y. And so what I find as my final result here is negative mg delta y, the change in y. That is y minus y naught. So if the work done is equal to the negative of the change in the potential energy, which I asserted at the beginning, is equal to the negative, or is equal to negative mg delta y, then what I find is that the change in the potential energy, delta U, is equal to mg times delta y. Now, a little detail to that, or a little thing that we commonly do, is realize that my gravitational potential energy includes within it an arbitrary choice of the initial gravitational potential energy. I choose what the initial y is. I choose it. It's in coordinate system. I choose. So I can make a choice that y naught is equal to 0. Therefore, u naught is equal to 0. Because if y naught is equal to 0, u naught is equal to 0. And then I have the gravitational potential energy, Ug, is simply mgy. Now, a very, very common thing that we do in our physics, realizing that the gravitational potential energy only depends on vertical displacement in the gravitational field, is we very commonly replace y with the height h above a reference height that we choose as 0 in a given coordinate system for the solution of a problem. I choose the height to be 0 wherever. So if I take my marker here and I set it on the tabletop, if I choose the tabletop to be 0 height, then the marker has 0 gravitational potential energy. But if I choose 0 height to be the floor, then it has some gravitational potential energy. That's a number that I can calculate. You say, Shai, that's a problem. You see sort of arbitrary definition. It could have any gravitational potential energy you want. Yes, but it will turn out that it is not the gravitational potential energy at any instant that matters. It is how much the gravitational potential energy changes. The name potential energy is kind of I think, a little funny name. I've never liked it. But the name potential energy makes a little bit of sense in this regard. If I have this pen sitting here on the table and I lift it, I am doing positive work. Gravity is doing negative work. The gravitational potential energy increases. So now we say it has more potential energy in the higher configuration than it did in the lower configuration. The potential energy is the potential to become kinetic. That's what's meant by potential energy. Sometimes I hear a statement, potential energy is the ability to do work. That's nonsense to me. I don't even get that. I don't know. I don't understand how that even makes any sense at all. No one can explain it to me in a way that I like. Potential energy is stored energy in the sense that because the work is independent of path, if positive work is done from position 1 to position 2, negative work is done from position 2 to position 1. That is, when a conservative force does work, that work, that is a quantity of energy, can be given back again to kinetic energy. This is why such forces are called conservative, because the work that they do can be given back again, so that energy ultimately, we'll find, can be described as a conservative quantity.